Well, so I'm going to do a brief introduction. So next speaker is Natasha Jaques, who unfortunately couldn't come for some COVID reasons. For the anecdotes, like last time, it's me who could not invited her, but it's me who could not attend because my daughter got born. Just the delivery started before her talk. So I hope like the next time we will manage to meet finally. So Natasha made her PhD at MIT Media Lab with Rosalind Picard in affective computing, and pursue with a senior research scientist position at Google Brain, and simultaneously visiting postdoctoral fellow at Bayer in Berkeley. And our talk is about social reinforcement learning. There you go. So let's hope it would work. Yes.
Hi, I'm Natasha Jaques, and today I'm going to be presenting about my work on social reinforcement learning. So when I like to think about what motivates my work, I like to think about trying to make an AI assistant that could help us with a bunch of everyday tasks. So it could do things like be physically in our environment with us in our kitchen, helping us prepare a meal. It could do complex tasks like helping us manage our calendar, and it could drive us to work. So if we think about an assistant that could do all of these things, what abilities are lacking in state-of-the-art AI that we need to make progress on before we can enable this? Well, I think if it's going to drive us to work, it needs to be able to coordinate with us in shared spaces, for example, on roads. But if we look at the state-of-the-art in multi-agent coordination, for example, in this DARPA robotics challenge, seems to be a few coordination problems here. And actually, they just lost that drone as a result of this coordination failure. So we still need to make some progress on coordination. And I think if we want this assistant to work effectively, we actually want it to be able to learn from natural interactions with us. So wouldn't it be great if your Roomba could understand your natural language commands, and it could understand your gestures and your social cues? But if we look at the state of the art in learning from human interaction today, we still see a lot of systems that are learning from manual button presses. For example, people filling out these cards saying how satisfied they are with Google's results. And finally, if we want an assistant that can do complex skills like helping us prepare a recipe, we actually need to make fundamental progress in terms of learning and generalization. So in order to do a recipe, you need a complex sequential decision-making over a long horizon and multiple complex subtasks. And if we want to deploy these types of robots to everyone's homes, we need really effective generalization. So ideally, we want an agent that we could train in a simulated kitchen and deploy it to everyone's kitchen in the world. But if we look at the state of the art in generalization today, we see that even in Atari, if we train in the Atari environment on the left and then just tweak the colors and the paddle size, the agent will utterly fail to generalize to this new environment. So we need a lot of progress in things like learning and generalization. And I'd like to make the case to you that actually social learning can help address all of these desiderata. So it might be obvious that social learning can help with social problems like coordination or even learning from human interaction, but I'd like to argue that it can actually help with fundamental issues like learning and generalization as well. And so what do I mean by social learning? Basically, I just mean learning from other intelligent agents that are present in your environment. And this is a very ubiquitous strategy in the human and animal kingdom because it can be very effective. So for even this little 1-inch fish, it can use social learning to generalize effectively to new environments by looking at where other fish are gathering to find a safe source of food. And in the UK, there's this fun example of birds that learn to open milk top bottles, not because each bird independently discovered this behavior, but because they could learn by observing other birds. And of course, many authors have argued that the key differentiator that humans have versus other animals is actually our social learning abilities. And it's those incredible social learning abilities that have led to our impressive cognitive, cultural, and technological development. So social learning can accelerate learning. Individual learning can be unsafe, error-prone, and time-consuming, but social learning lets you stand on the shoulders of giants. And so my research works on social reinforcement learning in two contexts. One, in multi-agent interactions where you're learning from other AI agents, and two, in human AI interaction where you're learning from humans. And I'm going to talk about both of these aspects of my work today. And to give you a broader overview of my work, I've worked on the more human AI side, where I've worked on detecting human social and emotional cues, then learning from those cues and interactions with humans, teaching multiple agents to coordinate with each other, multi-agent social learning specifically, and setting up multi-agent systems such that they give rise to the emergence of complex behavior. And so for today's talk, I'm going to talk about those two aspects. And I'll start with the social learning aspect first, because I think it kind of gives a lot of context what I mean when I say social learning. So is social learning just imitation learning? I mean, I said it helps you stand on the shoulders of giants, but so does imitation learning. If you want to quickly acquire behavior from something an expert already knows how to do, you could just use imitation learning. So imitation learning is just supervised learning on a curated data set of expert state action pairs. But the issue with imitation learning is that you're given this data and you basically copy it exactly. So we know that imitation learning performs poorly if the data is going to come from imperfect experts, because you're indiscriminately copying all of the actions in the data set. And so here in this figure, you see a comparison between imitation learning methods and offline RL methods, which are able to find a better policy on top of the imitation data. And the other issue with imitation learning is the resulting policies are brittle and they don't generalize well. So if you go off of the support of the state action data set that you had to copy, your policy doesn't know what to do. Whereas reinforcement learning can explore beyond that and potentially improve. And I'll show the brittleness of imitation learning in some results that I'm about to present. So when I'm talking about social learning with multi-agent RL, I'm talking about something a little bit different. Here, I'm thinking of you're in a naturalistic setting where there are other agents present in the environment, but they're not necessarily motivated to teach you. So imagine real world settings like the human world. There are a bunch of other agents running around, but they're just going about their business. They're not trying to actually teach you any information or provide you a curated data set of what you should do. So this is true of settings like autonomous driving. There are other cars on the road, and some of them are really intelligent and might be doing the right thing, but some of them actually might be bad drivers. So you don't want to indiscriminately copy everyone. What you actually want to do is have a social learning ability to determine who is a good model that you should be learning from and in what context. And so basically, social learning is the skill of learning how to acquire information from other agents. And I would argue that this skill actually allows you to adapt effectively to new environments. So if you know how to acquire information from other agents and you're put in a new environment, like let's say you go to a new coffee shop and you've never been there before and you're not sure how you're supposed to queue for your coffee. Do you order at the counter? Do you sit down? You can learn that by just observing what the other agents are doing, what the other people are doing at the coffee shop. So the skill of social learning actually helps you generalize to a new environment that has other agents in it, because you can watch the other agents to figure out what you're supposed to do. And so that's what I'm going to try to show to you today. So let's talk about this first project, which I did with a student named Kamal Endus, and he's great. The idea here was we wanted to study how much vanilla model-free RL agents actually engage in social learning. So we put RL agents in a partially observed multi-agent environment with an expert that was constantly demonstrating the correct, highly rewarding behavior in that environment. So the expert is constantly showing exactly what actions you need to take to score a high reward in this environment. But it was a sparse reward, difficult problem. And we operationalized the definition of checking if the agents are engaging in social learning by comparing the performance of agents that were in that environment with the expert to agents that trained alone since the beginning. So this is what you see. The expert performance is shown in black. The agents trained with the experts are the social agents in purple. And the solitary agents are shown with a pink dashed line. And what you can see is that there's no difference between the social agents and the solitary agents. And so this shows that basically vanilla RL agents have no benefit of social learning at all. So they're much dumber than this little 1-inch fish we talked about. So in this work, we just did a simple fix to address this problem. We said, in addition to our agent deciding on its RL policy, it's just going to have an auxiliary prediction loss to predict its own next observation. And what's interesting is that implicit in being able to accurately predict the next observation, you have to predict what the other agent is going to do, because you need to predict where they are in the frame. So this was enough that it forced the representation of the agent to encode something about what the expert was doing. And what we saw is that this simple fix actually allowed our agents to successfully learn socially from the experts. So that's that green line you're seeing here. They've now, just with this auxiliary prediction loss, reached the performance of imitation learning agents, which were given direct access to the state action pairs of other agents, whereas our agents don't have that. They're just in the environment with the expert. And so this is kind of cool. You can say you can learn effectively from other agents in your environment, even if you don't have access to their data. But you might say, I might have access to their data. Like in autonomous driving, I probably do have a data set of the state action pairs of a bunch of drivers. So why is it worth it to do this social learning approach rather than just doing imitation learning? Well, let me show you this. So what we're seeing here is the generalization performance of both imitation learners, RL agents, and social learners to a series of new environments that they've never seen before. And so what you're seeing is in the new environment, this green line is an expert that's been trained in that new environment. So in each new environment, there are experts running around that know how to do the task. The original RL agents in orange generalize poorly to the new environments. We know RL can be kind of brittle in that way. So do the imitation learners. They're in fact extremely brittle, much more brittle than RL. But the social learners are shown in purple here. So they actually perform pretty well across all three environments. And why this is happening is they basically learned a policy about how to acquire information from other agents that they can deploy in a new environment to figure out what they're supposed to be doing. So I think this is pretty interesting. There's also another interesting finding I just want to highlight, that we can show that social learning enables the agents to discover skills that they would never have discovered if they'd trained alone since the beginning. So what you're seeing here is the performance of solo learners as the line on across the bottom, and then agents that were trained with either only social learning or a mix of solo and social episodes. So in the solo episodes, the agent is alone. In the social episodes, they're with the experts. And what you see is that as you use social learning, basically the agents start to discover a behavior from learning with the experts that they're never able to discover if they train alone. But if you continue using only social learning, then the agents become dependent on the presence of the experts, and their performance in the solo environment decays. So it actually gets worse. But if you do this mix of solo and social training, we see that the agents trained in that mix preserve their performance in the solo environment using the information that they gain from training with experts. So essentially, they're acquiring a skill from the experts, which they are able to maintain and deploy when they're alone, which is fun. But this method was a pretty simple way of helping the agents to engage in social learning. So can we develop more sophisticated methods for doing social learning? And so this was a project I did with another student named Angelos Philos, who's great also. And here we're going to use successor features to help with social learning. So if you're not familiar with successor features, I'll just give you a quick rundown. As you know, in RL, we're trying to, estimate our total expected future reward, which we can parameterize as a Q value, which is the reward expected from being in a particular state and taking a particular action. Successor features decompose this into two components, a psi component and a W component. And so what psi is doing is essentially doing all the hard work that we have to do in RL of estimating what's going to happen in the future. So psi is going to estimate over the course of an episode how much of these state features phi we're going to accumulate. So imagine we were in a grid world and we just had to pick up different types of fruits. So apples versus bananas. You can imagine phi would say, at a given time step, did I pick up an apple or a banana or nothing, right? So it's just a bit vector. Psi would say, over the course of an entire episode, how many apples and bananas am I going to pick up following my policy, right? And then W is just a preference vector. So this stays the same across every episode, and it just describes how to map those state features to reward. So if the agent prefers bananas twice as much as apples, we can just take that 2-1 preference vector and multiply it with our, psi and compute our Q value, which is our total expected reward from what's going to happen in the future. So why is this important to do? Well, the nice thing about successor features is it lets you adapt very quickly to new preferences, right? So if at test time I say, look, you've learned to pick up twice as many bananas as apples, But now I want to change your preferences to pick up twice as many apples as bananas. So I'm changing W to 1, 2. I can instantly compute which action will lead to the highest payoff under that new reward using my existing psi. So I can do a very quick adaptation to new preferences. So this actually helps a lot with generalization. So that's nice. So what we wanted to do is apply the same concept to learning from other agents. So what we're going to do is we're going to model ourselves, the ego agent, as well as all of the other agents in our driving environment, all the other agents that are present on the road, using this successor features approach. So every agent is going to have this estimated psi that's estimating what state features it's going to encounter according to its policy, and this W, which are essentially its preferences. So we can learn the ego agent's successor features or successor representation just with RL as normal. And for the other agents, we can model them with maximum entropy IRL. So essentially we say the other agents are soft optimal. We observe the probability of the actions that they're taking, and we assume that an action is exponentially more probable if it has a higher Q value, or if the successor equation is higher. And so we can use this to infer the successor representation of the other agents. But what's cool about that is then we can say, look, I inferred the other agent's preferences, but I actually don't care about their preferences. I only care about my own preferences. So what I can do is substitute my preferences for every other agent's preferences, and then ask myself, using this generalized policy improvement idea, could I get a higher reward if I just acted like one of the other agents according to my own preferences? So basically at each time step, I say, look, if I were to take the action, I'm going to take my preferences and combine it with agent 2's psi, and that's going to give me the recommended action that agent 2 would take if it were optimizing my preferences. And if I compute that that action has a higher payoff than my own action, then I can selectively imitate the other agents to the degree that I compute it would pay off for my reward function. So that's pretty fun. But of course, in order to get this to work, we have to choose a phi in a very specific way. So you might remember, if we look at this equation for psi and phi, psi is policy specific. So it's counting up what's going to happen in the future if I'm acting like a particular policy, like agent 2. But phi is actually policy agnostic, right? It's just the features that are happening at a single state. So what we did in this work is we say, look, all of the agents can share the same underlying feature representation phi. And that's going to allow us to swap our preferences with other agents' preferences. We can ensure that those are compatible. And we can build up every agent's psi using the same phi. And so we get a lot of data. As we're trying to model all of the agents in the environment, we get a lot of data that can help us learn that phi. And whenever we learn something about one agent, that actually improves our modeling of the other agent through improving this feature representation phi. And we learn these phis and psis using this inverse temporal difference loss. This basically looks like a Bellman error, but without rewards. And we can also improve our phi with rewards when we're acting as the ego agent. So as ourself, the ego agent, we can interact with the environment and get rewards. We can use that to further refine our phi. So we basically get a lot of signal about how to train this feature representation. You can think of it as extracting a sort of a universal feature representation that's capable of describing any agent's behavior. It's extracting all the features relevant to describing any agent's behavior. And so to zoom out for a second from the math and give you the higher picture, basically what we're doing here is we are creating this feedback loop where the more you learn from others, you can selectively imitate their actions and choose actions that will lead to a higher payoff for you based on copying other agents when they're relevant. And then the more you act in the environment and gain experience with the environment and observe rewards, you can further refine that shared feature representation, which improves your modeling of others. So the more you interact, the more you model others, the better you model others, the more you can steal their actions and get better reward. And so what's nice about this is we tested it in a variety of environments. So some autonomous driving environments, a grid world environment, and a more visually high dimensional environment called fruit plot. And what we see is pretty interesting. So in the case where all the other agents are relevant to what your task is, so essentially all the other agents are doing the exact same task as you, then the best thing you can do is imitation learning. That's going to learn the fastest, but our method learns pretty quickly. It learns more quickly than RL methods. In the case where the other agents on the road are doing something exactly wrong, like parking on the highway, if you imitate them, you'll do catastrophically poorly. So you see imitation fails in this case. The RL methods still do well, and so does our method. But in the realistic case where you're in a multi-agent environment where some of the agents are doing something relevant, but many of the others are doing something irrelevant, then our method outperforms both imitation learning and RL because it gets the best of both worlds. And the nice thing is we get some side benefits of this method. So as part of doing our method, we're implicitly modeling what other agents' actions are going to be next. So we're being able to predict other agents' actions. And we see that versus different imitation learning methods, our method can more effectively predict what the other agents are going to do on a held out test set, especially when the other agent's task changes. And our method works as an effective inverse RL method. So we can infer the reward function that other agents are optimizing and then effectively optimize it ourselves. And finally, our method improves generalization. So as opposed to imitation learning, where it can take up to 100 new episodes to adapt to successfully imitating an agent in a new task, our agent can adapt in one shot. So this is actually pretty cool because let's say during training, you've only ever been asked to pick up bananas in this, fruit picking world. At test time, but you've observed another agent picking up apples. At test time, our method is able to adapt one shot to the apple picking task because they've already observed a policy that's good at picking apples, and they can just switch to it by adjusting their preference vector W. So we get a little bit closer to this 1-inch fish in terms of generalization. So in conclusion, social learning is a powerful mechanism that can help RL agents rapidly adapt to new environments and learn complex behavior. All right, so let's go to the last part of the talk. So in this part of the talk, I want to talk about learning from human AI interaction, or learning from interactions with humans. So I think I'll start with this obvious example about why you might want to do this. So this is a real interaction someone had with their Alexa. They say, Alexa, what's the right way to Walmart? And Alexa says, the right way to spell Walmart is W-A-L blah, blah, blah. So this is obviously not what the user wanted. And I'm going to bet you that the next thing that they say contains some hint that they were frustrated, whether it's in their tone of voice or their facial expression. There's some clue there that Alexa could learn not to do this again. And yet, the way we often train AI systems is still focused on using these types of manual button presses for the human to indicate whether they were satisfied with the results. But if we were able to learn from this type of social feedback, like facial expressions, tone of voice, we could learn much more ubiquitously and naturally. So people are giving us these signals for free anyway as they're interacting with AI systems. So if we could just pick up on them, we could learn more effectively. And so this is the focus of a project that we worked on learning from implicit human feedback and dialogue. So what we did was we created a system where we could deploy dialogue models to the internet and have them interact with people live. And here's an example of an interaction. And what you see is that when the user or when the bot says something that doesn't make sense, like sorry to hear, the user says, that doesn't make sense. And we can actually detect from the text itself that this is a good clue that the bot is doing something wrong. So for example, we can detect a negative sentiment from that text. And that can serve as a negative reward we can use to train the bot not to do this again. Similarly, when the conversation is going well, the user's sentiment is positive, indicating that the bot is doing a good job. So we can use this type of implicit signal in the text itself to try to train the bot to have better conversations. And so essentially what we did was, as I mentioned, created this online platform for collecting this data. And we did this by first pre-training a bunch of dialogue models. We had to scrape some new data sets in order to do this. And we put these models online. And as you can see in the interface, we include a few different features. So we included an upvote, downvote button. So the user could manually indicate whether they thought the bot was doing a good or a bad job with that specific utterance. And we also included what sentiment we were detecting from the user. So we showed that back to them to say what the bot was thinking of the sentence that the person just said. And our hypothesis is that trying to train the bot based on these explicit manual upvotes isn't going to scale as effectively as training on this implicit sentiment from the user. Because while the upvotes are the ground truth, the user's just not going to want to provide them very often. In order to do that, they have to deviate from the natural chat interface that they would normally be using and go out of their way to provide that signal. Whereas the sentiment is something that we get in every piece of text regardless. But in order to do this work, we actually want to dig a little bit deeper and go beyond just sentiment. Were there other implicit cues that we could use from the text to determine whether the conversation was going well? So we scraped the literature on both dialogue models and human-human conversations to look at what kinds of signals are indicative of an empathetic and engaging conversations. And we came up with a bunch of different options, and we looked at the relationship between these metrics and the upvotes and downvotes that we received in our initial data collection. And so we did treat the upvotes and downvotes as ground truth, and we actually found that these signals related reliably to them. So essentially, asking questions turned out to be related to getting upvotes. We found this from the human-human conversation literature. It's supposed to be an important active listening skill. Reducing repetition on the part of the bot is very good because that was from the dialogue model literature and it proved to be true. And finally, we found that really engaging with the user is important. So eliciting positive sentiment from the user had a strong relationship with good conversations and eliciting laughter. And finally, just staying on topic with the user by maximizing the similarity between the bot sentence and the user sentence, both in terms of the sentence embedding and word similarity. So these were the metrics that we stuck with for how to train a good conversation model. And so basically what we wanted to do is use reinforcement learning to actually learn to optimize these metrics by putting our bots on the web and having them interact with humans. So basically, instead of your normal RL paradigm where the agent is interacting with a simulated environment, in our paradigm, the agent is actually interacting with a human. The human is the environment that's providing rewards based on whether they enjoyed the conversation. But wait, did I just say I wanted to put an agent online and have it interact with humans on the internet to teach it how to talk? I think we've seen how badly that can go in the past. So we decided in the context of this project that we actually needed to carefully test any model that we trained offline before deploying it back to humans. So we can't have it learning online from interacting with humans about how to talk. And so what this necessitated is actually to do fully offline learning, which means that our normal interaction or exploration part of the RL loop is broken. So instead of being able to explore to find which actions lead to high payoff, we have to learn entirely offline. So we're in this off policy from static data, batch or offline RL setting. And this is a very challenging setting because a lot of RL algorithms are built such that they're optimistic in the face of uncertainty, and the exploration is actually key to refining the estimates that they learn. So I'll give you a quick illustration of why offline RL is hard. So let's say you're this little robot and you're trying to learn to walk to this red flag, but you're only given the data in a single batch of data, and the probability that you see a state in the batch is shown in yellow here. So basically anything in this region that's white off of this yellow support is not in the batch data. So the issue with offline RL is that if at any point your policy is initialized or learns that going into this region of unexplored space is a good idea, it has a high estimate for this region of space, it has no way to refine that estimate because it doesn't have any data from that region of space. And actually that bad estimate will propagate backwards into all of the preceding states, right? Because we're trying to estimate our total expected future reward. And so if we ever think this is valuable, that incorrect estimate is going to be propagated into all the preceding estimates. So basically, estimating value in offline RL can be arbitrarily bad. But we solved this with a very simple thing. We just said, let's add a KL constraint so that we say that as the agent is learning its RL policy, it should actually minimize the KL divergence between its policy and the support of the batch data. So basically, search within this region of highly rewarding behaviors here in order to find the optimal policy. So to put that in math, basically we're just doing KL control from a pre-trained prior model of probability of A given S. And this can be learned from the batch data, or in the case of language, we actually have a really good model of which actions are acceptable given the state, because this is just our pre-trained language model. And so what we do is we say, instead of just maximizing our expected reward as we would normally do in RL, we're going to minimize the KL divergence between our RL policy and this pre-trained model, or our language model. And so when we're estimating the Q value, this amounts to adding two simple terms. We simply subtract the log probability of our policy. So this is equivalent to doing entropy regularization, which is a good idea to do in dialog anyway. And we add the probability under the prior. And so this just says you're going to get a reward if you take actions that look probable according to the language model. And we do a few other tricks, which you can check out in the paper if you're interested. But let me first establish that this is an effective offline RL method. So this idea of KL control from a model of what's probable in the batch is actually performing well across a bunch of OpenAI gym environments and outperforming batch constrained Q-learning, which was the competing offline RL method at the time. But let's see this in the context of dialog. So what happens if you don't do this and you just try to use offline RL on dialog data? What you see is that your model starts saying things like, where did you say to me? You want to talk to you about you? So it's basically using very unrealistic sentences. So it doesn't know what is a realistic sentence once it's off of the support of the batch data. So it can become increasingly unrealistic. And it's just trying to maximize the rewards we gave it by, for example, exploiting asking questions, because that's one of the simplest rewards that it's able to do that we gave it, instead of actually doing something more sophisticated. But what we see is that when you add KL control, the model says things like, hey, I hope you have a great day and I wish you the best. So through this constraint, it's now learned to use more realistic language. But in order to optimize these rewards, for example, eliciting positive sentiment, it's learned to be very cheerful, polite, and supportive. So we inadvertently came up with a metric that trains the bot to be Canadian. But what we see is that when we deploy these models to new humans at test time, so they're now back on the internet and they're interacting with a new set of humans, we see that our models are able to elicit significantly higher human reward from the humans. So they're able to elicit more positive sentiment and more laughter than any of the baseline methods, including the original language model. So we see that we're able to effectively learn with RL using this technique. If we compare how optimizing each of the different reward functions in isolation affects the human evaluation. Basically, we have a human evaluation where they're rating the bots on the quality, fluency, diversity, etc. We're also looking at the votes, the upvotes, downvotes that each bot received, and the amount of human reward they elicited. What we see is that, as we suspected, optimizing for eliciting positive sentiment or displaying positive sentiment leads to the highest quality and the highest human reward. So we're seeing that affect is important to good conversations, which was nice because this is keeping my advisor of the affective computing group very happy. But in addition, as we suspected, if you try to optimize only for the manual upvotes and downvotes, you don't do very well. So you don't get a high conversation quality and you don't elicit much human reward. So even though this is kind of the ground truth signal of what conversations or what utterances the humans enjoy, it's not sufficient to be able to train a good model because it's just too sparse. So when we instead use these types of implicit signals like sentiment, we can do much better. We also looked at human evaluation comparing each of the different models. So the baseline offline RL methods that we compared to. And as we suspected, both in terms of the quality, the votes, and the human reward, the KL control methods are significantly outperforming the RL baselines. But there is a caveat to these results. In terms of the original language model that we used as our pre-trained prior, the RL methods do significantly outperform it in terms of eliciting human rewards, but they're actually not that good in terms of beating this model in terms of the conversation quality. So the original language model, the humans actually rate a slightly higher quality, which is somewhat ambiguous. So that could mean that our reward functions are not sufficient to really measure what is a high quality conversation. But I think there's something else going on here. In addition, we don't have that much data from this small human study, but I think there's something more profound, which is that that model was learning to optimize these rewards by modifying the probability of outputting each and every word. So you're basically learning how to maximize things like user satisfaction at the word by word level. And that's actually a very hard learning problem. So what we did in some follow-up work is we instead tried to learn the rewards at the sentence level. So we had a hierarchical sequence-to-sequence model where there's a sentence level embedding that conditions a word level decoder. And by using continuous control to modify that sentence level embedding, we can actually optimize for all of these same rewards that I just discussed at that sentence level. And we see that this actually resolves that issue. So now what you're seeing is not only does our RL model outperform the RL baselines like reinforce and VHRL, but what we see is that it actually outperforms both a transformer language model and our original language model that we base this on. So both in terms of human ratings of quality, as well as the amount of time people spent talking to the bot, which we're taking as another implicit signal of whether they enjoyed it in this work. A fun thing to do is to look at, how well these models can optimize for these different rewards. So if we look at our transformer baseline, this is a transformer trained on a pretty small data set, so it doesn't always have the best performance. But we see that our RL model can do things like optimize for eliciting sentiment, which we've seen. I'm in a sunroom a lot, and it's a great feeling. It can optimize for asking questions. So what do you do for fun? We've seen this. It can minimize repetition, which is important to maintaining conversation quality, as we saw. And it can do this more effectively, again, at the sentence level than the word level. So in this conversation, the user says, "How are you? I'm a reservoir engineer. Cool, I am still in college. Today is my first day of vacation." It's nice. It can also optimize the semantic similarity, so staying on topic with the user. So in this conversation, the user mentions Ed Sheeran. The bot says, "What genre is it?" And then the bot asks for any recommendations. So it's staying on topic with what the user is saying. And finally, and I think most importantly, in this work, we also discussed the idea of minimizing the toxicity of the model. So whenever you're training these dialogue models on large-scale internet data sets, we know that they can exhibit biases, they can exhibit racist and sexist language. So what we did was we trained a detector, a classifier that says, is this language toxic? And then what we can do is use that as a reward function for our RL model to try to minimize that toxicity level. And we see that our model is able to do this pretty effectively, and we have some results of that in the paper. I think this is actually really important to emphasize why you might want to do RL on top of language models, right? There might be some non-differentiable metrics that are really important for you to minimize, like toxicity, that RL gives you the ability to do that. So whatever metric you can decide should be a quality of your text, you can use these RL methods to optimize for that. All right, so in conclusion, this is the first work to propose KL control from a pre-trained prior as a way to handle offline or batch RL. But the key thing here is that we're using reinforcement learning to improve based on human feedback. And we showed that learning from implicit signals from the human, like sentiment, scales better than learning from manual button presses. And as I mentioned in the last slide, and the other thing to note is that RL allows you to optimize for any arbitrary metric you can code up. So if you want to do something like reduce toxicity, this can be a really useful tool. All right, so in conclusion, social reinforcement learning can improve coordination with other agents, human AI interaction, as well as fundamental issues like learning and generalization. So I'll stop here and take any questions. Thank you.
All right. So unfortunately we can't take questions, but we hope you enjoyed her talk. And
I was making a joke that usually like when people say, actually it's not a question, but more a comment, at least you can do that if you want. So, but well, we can also save time for the roundtable.
Yeah, I think Natasha talk brings up a lot of issues that will definitely be